I'm pleased to introduce today's speaker, Dr. Georgy Falster from Washington University in the US, where she is a postdoctoral research associate. And the title of her talk is Using the Stable Isotopic Composition of Water to Gain New Insights into Global Hydroclimate Variability Through the Common Era. So hopefully I've done all of that correctly, and I will now mute myself. All right, go ahead, Georgy.
Excellent, thank you. A thumbs up if my screen is all good. Yes, good, excellent. All right, sorry about the slightly unwieldy title, but yes, so many thanks to the 2K network for giving me the chance to share what ISO2K has been doing for the past 6 years. I'll be presenting work that's been done by a very large number of people working very hard for many years. So I've listed the ISO2K project members here, along with our leader, Bronwyn Kodicki, who you just heard from. And so in the seminar today, or if you're watching on YouTube, I'll start with a bit of background, which will tell you why ISO2K was a thing that needed to exist, along with a brief divergence into some water isotope systematics. Then I'll show you what ISO2K is. And then I'll go through some of the new findings that the database has let us uncover, in particular, how our data syntheses reveal that global mean temperature is the primary driver of the isotopic composition of the global meteoric water pool on millennial timescales, but the atmospheric circulation plays an important role in spatial variability on shorter timescales. And then I'll just zip through some new analyses that are in the works and finish up with some thoughts on what is next for the ISO2K community. So first off, the question, I guess, is not so much why do we care about hydroclimate variability, but more, why don't we already know more about the response of global hydroclimate to for example, global temperature change, and particularly over the Common Era, where Pages 2K have done a really excellent job of constraining temperature variability, both in space and time. And possibly you caught a bit about that at the last Pages 2K seminar from Rafi Newcomb. But here, just as an example, I'm showing on the left the Pages 2K Global Temperature Reconstruction Ensemble, and on the right, some summaries of spatial variability within that global mean change. But one of the reasons, I guess, that hydroclimate is maybe not so far along is that, well, it's complicated. Hydroclimate is a thing that encompasses a lot of variables. When considered, I guess, in terms of global mean changes in precipitation and evaporation, maybe hydroclimate is relatively straightforward. In the global mean, we expect and indeed see a strengthened global water cycle with increased global temperature. But this sort of obscures the regional scale hydroclimate processes that are really important for the sort of understanding the boots on the ground impacts of climate change. And these changes are more complicated to tease out, particularly over the continents, which means that there is no sort of single useful hydroclimate variable that we can just go ahead and reconstruct for the past 2,000 years. And so we turn to a variable which has the potential to hold information about many different aspects of the global water cycle, including things like moisture source and transport length and path, and hence seasonality, convection style, rainfall intensity, below cloud processes, and many other things. And this variable is, of course, the stable isotopic composition of precipitation, whether that be rain, hail, or snow. And just a quick crash course in case we have some non-isotopists listening in. Water is made of hydrogen and oxygen, both of which have multiple stable isotopes. In the case of both hydrogen and oxygen, the ratio of the most common, light, to the second most common, heavier, isotope preserves information about environmental conditions every time that water changes phase. For example, condensation of vapor to rain. So to use my favorite illustration here, we have two cats standing in as proxies for two oxygen isotopes. So in the top, in the green, we have Fluffy, who is a relatively svelte 18, a sort of a lighter, more active cat. And then we have the more majestic, weightier Captain Sprinkles, a lazier cat. Now, if we have a pool of liquid water with a particular ratio of Fluffy to Captain Sprinkles, or delta O18, when some vapor evaporates from that liquid water, the lighter, more active cat, Fluffy, oxygen 16, will preferentially go into the vapor phase. Whereas Captain Sprinkles, the weightier isotope, will prefer to stay in the liquid phase. And both the amount of fractionation and the absolute isotopic composition of both phases depends on various things, including the original isotopic composition of the liquid water pool, as well as the temperature and relative humidity at the point of evaporation. So I hope you can see then that it's possible for water isotopes to preserve information from any process involving a phase change, including evaporation from some particular oceanic source, moisture transport and cloud formation, and any other processes that happen as a parcel of moisture evolves, precipitation and solid cloud processes, and also moisture recycling that happens on land. And so changes in any or all of these things affect the ultimate isotopic composition of precipitation and subsequent waters. So there is a lot of information stored in water isotopes, whether that be from precipitation directly or whether precipitation ends up like soil and groundwater, lake water, surface seawater, etc. And what this means then is that it is possible for water isotope data collected even at a single site to contain information about regional or even basin scale hydroclimate processes. So for example, here I'm showing Jessica Merman's 5-year daily precipitation delta O18 record from Malaysia. So this red cross here, I hope you can see my mouse. Where on the left, we have daily precipitation amount regressed on rainfall amount across the Pacific. Then on the right, we have the isotopic composition of that precipitation also regressed on precipitation amount. So you can see very clearly in this case that precipitation isotopes hold a lot of information about large scale precipitation patterns, ENSO in this case, even when precipitation amount in the same location is really only correlated with local precipitation. And so this example, I think, really nicely highlights the power of water isotopes in understanding regional to basin scale hydroclimate processes, even from relatively few data sets. So on now to how this can help us to understand hydroclimate in the Common Era, and indeed one of the big motivations behind ISO2K. And that's that water, with all that information stored up in its isotopic composition, can be preserved in many different paleoclimate proxy archives. And this might be in their carbonate in the case of like corals and speleothems, lake sediments, or cellulose in the case of wood, or literally preserving that precipitation in the case of glacier ice. And in ISO2K, we include all of these and more. And so that was one of the goals of ISO2K, was to gather up all that water isotope information from all these different archives and store that information in one single database where it can be interpreted together, so that we can holistically, I guess, assess Common Era water cycle variability on scales up to and including global. Okay, so now we have covered the why. For those interested in some nuts and bolts, I will whip through exactly how the database was constructed. So in essence, ISO2K, sort of the team, consists of sub-teams of archive experts, which is to say people with expertise in speleotherms or lake sediments, corals, marine sediments, etc., who worked together in subgroups initially to collect data. So that's the isotopic data, and the chronology and any other supporting or ancillary data, as well as a huge amount of metadata, which we entered into giant spreadsheets, which in reality looked a lot like this for several years. So just getting data, entering it into the database, pulling metadata from papers, and then triple and quadruple checking that we'd entered all that data correctly. By metadata, that includes sort of relatively straightforward things like the latitude, longitude, elevation of a site, as well as more in-depth things like the seasonality of the record, information about how exactly the data were collected, and the physical and climatic interpretations of the record, but all translated into standardized terminology to allow for robust meta-analyses. And we did this for hundreds of records, as well as screening out records that didn't meet our criteria for inclusion, things like the resolution and length, which varied by archive, chronological control, and whether the data were publicly available or if we could get it straight from the author. The team did also meet regularly for the first 2 years of the project, entirely over Adobe Connect. We all met for the first time in person in Zaragoza in 2017 at the Pages Open Science meeting, where we had a really great session of sort of hackathoning and brainstorming. And then it was back online for really the remainder of the project. We did have quite a lot of workshops and hackathons and mini retreats, but these are all virtual. And I mean, I know it maybe seems like a bit less of a big deal given the year we've just all had, but at the time we were quite proud of all the emissions that we saved by not meeting in person. Okay, so that is some background to give you a feel for who ISO2K is and how the database came about, but what does ISO2K actually look like? And I know that this is something that can seem a bit murky to newcomers who've not been sort of actively involved. So in essence, it's an extremely thoroughly metadated database of proxy records for the isotopic composition environmental waters through the common era, very straightforward. So it could be seawater, rainwater, snowwater, lake water, groundwater, anything that is captured and stored by a paleoclimate archive. And this data is stored in the Lipid, which is the linked paleodata format. So then we can say that the database is a collection of lipids in a very standardized format with internally standardized terms. In practical terms, you can download it here from the Lipidverse. I've got the link in the bottom left there in a serialization for the language of your choice, as long as that language is R, MATLAB, or Python. And at least one of these works for Julia as well. Just very quickly, here's a bit of information, a summary of the Lipid format that ISO2K records are stored as. Lipids are extremely useful and quite easy to wrangle. And if you don't find it easy to figure out how to work with a lipid, there are lots of helpful materials to help you navigate the database. Or you can ask an ISO2Ker who codes in your language. We also published the database along with the example scripts of how to get started. But essentially an individual lipid file, so there's one for each site, stores practically everything you could ever need to interpret the data. And if there's something that isn't there, then there's also all the publication information bundled in so you can figure it out. But there's two sort of high level groups. There's the paleodata tables, which is the isotope measurements on their single published chronologies and all metadata pertaining to the isotope information, the isotope data. And then there's also chron data. So this is the raw chronological data that was used to make the chronology, things like radiocarbon or lead-210 measurements. These either came from the publications or directly from the authors, many of whom very kindly dug data out of the depths of their hard drives. And because we include this raw chronological data, this means that you can make and then store actually within the lipid age depth model ensembles, which can be used for later data analysis, but a bit more on that later. For much more information on the lipid format, you can watch Nick Mackay's Pages webinar from 2018 that I've written the link to down here. Okay, so here are just two of the key metadata fields in the database, because I'll be referring to these in the rest of the talk. So the first is the inferred material, or what is the particular environmental water that the archive preserves the isotopic variability of. So is it reflecting variability in lake water or soil water, groundwater, whatever. Regarding the second field, well, of course, water isotope proxy records can have many different primary drivers of variability. And we summarize these in a field called isotope interpretation, which answers the question, what was the primary driver of isotopic variability in that proxy record? Is it the isotopic composition of precipitation? Is it ambient temperature? Was it precipitation amount or evapotranspiration? And all the entries to these fields are in standardized terms. Of course, there are many, many, many other metadata fields, things like the measured material, if that was carbonate, ice, cellulose, seasonality, direction of interpretation of the record, the climatic interpretation, which is the things that the authors of the data interpreted their record to mean, for example, amount effect or monsoon strength, changing moisture sources, and of course the archive type. So if it's a speleothem, coral, glacier ice, lake sediment, etc. For an exhaustively detailed description of all metadata fields, you can read the wonderful database description paper that I've given the DOI of here. But having these metadata fields with their standardized terminology allows users to filter records according to what can be sensibly analyzed together, as well as allowing data from diverse proxy types to be synthesized together, but informed by the knowledge of many experts. So here is a map from the database description paper showing all ISO 2K sites, and here colored by archive type. And the bottom panel shows the temporal data availability. So we allowed non-annually resolved records to avoid the sort of a severe data drop-off that could happen back at the start of the Common Era if we only included annually resolved records. But now here are a couple of maps still showing all the sites in the ISO 2K database, but now coded by their entries in those two metadata fields I just described. So the map on the left shows the inferred material, or the particular environmental water that the proxy archive reflects the isotopic composition of. For example, these purple triangles are mostly corals, and the inferred material is, of course, surface seawater. And then we've got in the yellow circles precipitation in the case of all glacier ice cores. The map on the right shows the isotope interpretation, which is a big one for our science results to follow. So here we have all the possible standardized isotope interpretation categories in the different colors, grouped into what we call the isotope interpretation supergroups, which are the shapes. So the triangle represents records where ambient temperature is the primary driver of isotopic variability, for example, temperature sensitive corals. P isotope in the teal diamonds is our shorthand in the database for the isotopic composition of precipitation. So this is where the isotopic composition of precipitation itself is the main driver of isotopic variability in that proxy archive. So this is all ice cores, as well as, for example, places with a dominant amount effect. And then finally, in the circles, we have effective moisture, which is our catch-all phrase for the relative amounts of precipitation and evaporation, and all related variables are like evapotranspiration. So a lot of lakes fit into this category, as well as some corals, for example. All right, so that's the database. Now onto some of the new findings that we have from all of this information. And this is all taken from a paper that we will be submitting in the next week or so. So first up, what am I showing you here? All right, so these are the 30-year binned composite records split by that isotope interpretation supergroup that I just went through, which is to say the primary driver of isotopic variability in that record, so those coloured lines. Compositing is just a fancy way of averaging all the records together. For comparison, the grey shading behind the composites is the Pages 2K global mean surface temperature reconstruction, and the maps on the right show the records that contributed data to each composite. I won't be talking about the temperature-driven records anymore, so actually you can ignore that bottom composite in red. So a couple of things to note here. It's fairly clear, I hope, that these global composites broadly track global temperature, at least on sort of multi-centennial to millennial timescales. And this is particularly the case for this p-isotope global composite, which is to say the composite time series, which is an approximation of the isotopic composition of the global meteoric water pool. And this actually remains the case even if we take ice core records out of this composite, because of course we would expect them to have some relationship with temperature. So to describe then this top row, another maybe clearer way, the ISO2K database suggests that the isotopic composition of the global meteoric water pool is positively correlated with global temperature on long time scales. So just bank that for a second. Shifting our attention briefly down one panel, this is the composite of effective moisture-driven records, and you can see that this has much higher centennial scale variability. Keep in mind that the effective moisture records are affected by things like evaporation relative to precipitation amount. And I'll be coming back around to this in a moment. But to dive a bit deeper now into this global temperature, global meteoric water pool relationship, we also see this relationship when we wrangle the data a bit differently and maybe even a bit more clearly. So here, what I'm showing in the panel in the top left here, the time series, this is the first principal component, so the underlying similarity, from a subset of the records that went into the p-isotope composite on the previous slide. In this case, only records that have data spanning the full Common Era with not too many gaps at a 30-year resolution. Oh, sorry, note that this delta preset up the top here is shorthand for the isotopic composition of precipitation, whether that be hydrogen or oxygen, which in the database is tagged as p-isotope. So that p-isotope PC1 is the purple line here on the top left plot, with global temperature again shown in the grey shading. And again, you can see that even with a subset of records, the first principal component of variability of records tracking the isotopic composition of precipitation closely follows variability in global temperature, at least at this 30-year resolution. The map, B here on the top right, shows the individual loadings of sites on that principal component. And you can see that almost all sites are positively correlated with that principal component, which is to say that delta 18 or delta 2H at that site increases with increasing temperature on long time scales, just as we saw in the composite, which provides support for this being a globally relevant mode. Now, in our soon-to-be submitted paper, we propose a few possible reasons for this. Our main hypothesis being that, let's see, in a warmer world, there is increased evaporation of ocean water to the atmosphere. And by definition, ocean water is about 0 per mil, BSMO, and hence disenriched relative to the atmosphere. So there are more oxygen 18s getting around in the global meteoric water pool simply via mass balance. We also have a sort of a secondary option here, which is that with a warmer surface ocean, we have more oxygen 18 in the saturated boundary layer, which is in equilibrium with surface ocean water, although this is probably of secondary importance given that evaporation is mostly not occurring in equilibrium. Interestingly, some things that we might expect, like increased Rayleigh fractionation along with increased rainout rates in colder times, we don't actually see a lot of evidence for in the database, in that the latitudinal gradients in the Little Ice Age and the modern period, which is to say the coldest and warmest parts of the Common Era, are actually pretty similar. So that's interesting. Right, so now onto the spatial variability. And for this, we are looking at records where the primary driver of variability is effective moisture, or the ratio of precipitation to evaporation. So that is the green line on this plot on the left, which here is again showing the first principal component of variability, but now only for the last millennium. Again, the map on the right shows the loadings of individual sites on that first principal component. And because PC1, you can see here, is more or less a monotonic trend, this makes the loadings relatively straightforward to interpret. So this is just the loading map now. So what we have then over the last millennium is a negative trend in delta O18 on the western side of the Pacific, indicating increased effective moisture or more precipitation relative to evaporation. And the opposite on the eastern side of the Pacific, where we have positive trends in delta O18 suggesting decreased effective moisture. The slope of the trend through the last millennium in individual records is also shown by the direction that these triangles are pointing. Now just remember that these records don't directly record effective moisture, but rather that it is the primary driver of the isotopic variability. Hence, a positive trend in delta 18 represents decreased effective moisture or dry conditions. If I've totally lost you, then please ask me about it at the end or drop me a line. There's a bit of mental gymnastics involved here, and I'm kind of zipping through it. Anyway, this trans-Pacific pattern here smacks quite strongly of the Pacific Walker circulation, which is the zonal component of atmospheric overturning circulation over the tropical Pacific. And this trans-Pacific effective moisture dipole is something that we do associate with the Pacific Walker circulation. To dive a bit deeper into this, now looking over the instrumental era, where we can compare findings from the ISO2K database with observations. So here I am showing the first principal component of variability of ISO2K effective moisture records, but here for 1850 to 2000. So that is the black line on the top right. The grey line on that same plot is the sea level pressure gradient across the tropical Pacific, delta sea level pressure, which is a commonly used proxy for the strength of the Pacific Walker circulation. So a stronger gradient is a stronger Walker circulation or more La Nina-like conditions. And lower delta sea level pressure is a weaker Walker circulation or more El Nino-like conditions. And so you can see that PC1 of the ISO2K effective moisture records really quite closely follows changes in the strength of this trans-Pacific sea level pressure gradient. The map on the left here shows the loadings of individual records on that first principal component in the colored points. Then the shading is the correlation of that PC1 with observed sea level pressure from HADS-LP. For reference, the contours show the correlation of the sea level pressure field with that sea level pressure gradient. That's a proxy for the strength of the Walker circulation. So this map is really just another way of showing that the primary gradient underlying effective moisture-driven ISO2K records is very similar to changes in the strength of the Pacific Walker circulation. We also see glimmers of this in isotope-enabled climate model simulations. So here in the second row, this is an analysis by Samantha Stevenson, who replicated this ISO2K principal components analysis for the historical period by using the soil water delta O18 field, which is sort of equivalent, from the isotope-enabled CESM last millennium ensemble, just using grid cells corresponding to the ISO2K sites. And again, you can see that PC1 quite closely tracks that trans-Pacific sea level pressure gradient, both in the time series on the right and the correlation map on the left. And because in models we have no data availability constraints, we extended that model analysis past the instrumental era to cover the full pre-industrial last millennium, but otherwise the same analysis. And so you can see that that relationship holds, at least in CESM. And so this is a major finding from the global synthesis of ISO2K records, that on multi-decadal to centennial timescales, spatial variability in effective moisture is strongly correlated with changes in the strength of the Pacific Walker circulation. Okay, so that's it for results from our upcoming global synthesis paper. Sorry if it was a bit of a whirlwind, but you can always ask us questions. So now I will share some first results from new projects that really show the power of the ISO2K database and also will, I hope, give you a taste of how it can be used. So first, some work that's being done by members of the ISO2K Coral team, led by Diane Thompson and Jess Conroy, in this case using Coral Delta O18 to reconstruct sea surface salinity, which in turn provides information about larger scale atmospheric circulation. And the reason that it's possible to do this is that sea surface salinity is linearly correlated with surface seawater delta O18, which in turn can be preserved in coral carbonate delta O18. It's the formation water. The complicating factor is that coral carbonate delta O18 is also influenced by the temperature at which the carbonate precipitates. So to infer past sea surface salinity, we need to find places where coral carbonate delta O18 reflects seawater delta O18 more than it does local temperature. So here are two figures from the upcoming paper by this group. The top row shows ISO2K coral records colored according to this parameter fraction seawater, which, let me get this right. It summarizes the extent to which coral delta 18 variability is driven by seawater delta 18 variance or the covariance of sea surface temperature with seawater delta 18. So places where seawater delta 18 and hence salinity can be reliably reconstructed are places with higher FSW. So that's the brighter red colored points in this top row, which are concentrated, you can see, in the Western Pacific warm pool. The second panel shows the same sites, but now colored by the partial correlation of coral delta 18 with sea surface salinity, taking sea surface temperature into account, and with the significant correlations outlined in black. And again here, you can see that the strongest correlations are sort of around the Indo-Pacific warm pool. So what this says is that these warm pool corals are really excellent targets for reconstructing sea surface salinity and hence for better understanding large-scale atmospheric circulation across the region. For any more details on any of this, please ask one of the ISO2K coral people. There's at least one other archive-specific analysis that I know of in the works. This is with Matt Jones and John Tyler and possibly others, looking at the controls on latitudinal gradients in lake carbonate delta 18. So the interplay between precipitation delta 18 and then evaporation, precipitation, groundwater input and so on. And so, I mean, what's really cool about these two projects is that the ISO2K, it doesn't only have to be used for these big multi-archive global analyses. It's also a really excellent repository of data for individual archives. Now, finally, this is a preview of some work we're doing here at WashU with an undergrad researcher, Flora. And so this now is making use of that raw chronological data, which I mentioned is included in many of the ISO2K Lipid files. So we're making age depth model ensembles that can be used in future analyses to account for chronological uncertainty. So just for an example, here on the left, I've plotted the carbonate delta 18 data from Lake Haik in Ethiopia on its single published chronology. By using the raw chronological data for this lake, which is in the Lipid file, I made a Bayesian age depth model here from the published radiocarbon and lead-210 age constraints, which are bundled in the ISO2K Lipid. I'm showing this lake in particular because it has really quite a nice chronology. So in this plot on the right, then I've plotted that same delta 18 data, but on 50 different realizations from that age depth model. And so in the original publication, the authors compare timing of inferred hydrological changes at this lake with those in nearby lakes and rivers. But you can see, I hope, that by including chronological uncertainty, even in a simple correlation analysis, this could make a large difference to interpretations of what happened at a site when. And just to illustrate that quickly and show the power of time uncertain analyses that you can do using ISO2K, I similarly made an age ensemble for a nearby lake that is also in the database, Lake Ashenge. And then tested correlations between those two time series using many ensemble members from both lakes, so running a total of 500 correlation tests. Now, simply running a correlation test on the single published chronology for each lake would tell us that there is no relationship between the two, so a correlation coefficient of 0.07. However, you can see on this plot, which shows the distribution of all the correlation coefficients from that ensemble correlation analysis, that almost 20% of the correlations were significant. So that's the green colored bars. And these are all where there are stronger negative correlations, which suggests that maybe there is a relationship after all. And you can run this sort of analysis in R using GeoChronR or in Python using PaleoClim. This isn't actually the specific analysis that we're working on here. We're working toward a sort of a unified series of superposed epoch analyses, investigating the hydroclimate response to volcanic eruptions in the Common Era. But that's very much still in development. So this is just an example to show how incorporating chronological uncertainty affects even simple calculations, and that this is very easy to do in the Lipid data format. All right, so that's mostly it from me, but what is next for ISO2K? And for my 2 cents, I mean, of course, water isotopes are not the only way to understand past hydroclimate. There are many non-isotope hydroclimate proxies, things like dust, lake levels, grain size in lakes, other assorted isotopes, elemental proxies, other runoff indicators, fire proxies, hurricane and flood deposits, pollen and diatom records, documentary records, glacier accumulation rates, so many. And all of these could provide a lot more nuance to our understanding of common era hydroclimate, not only in terms of precipitation and evaporation, but also the dynamical drivers of hydroclimate and the statistics of extremes, things that would also be very useful for comparing with model outputs. There have actually been some toes dipped in these waters already. There was a Hydro 2K workshop in 2016 and this great review article published 4 years ago. There's also the Coral Hydro 2K group and some excellent hydroclimate synthesis products like FIDA, which is the, the hydrodynamics data assimilation product. But as yet, there's no actual Hydro 2K database. In fact, when you go to the Hydro 2K part of the Pages website, this is what you find. So maybe now that ISO 2K has really come into its own, it might be time to sort of resurrect a Hydro 2K of this type. Of course, this would involve some very careful planning in terms of how all that data could possibly be manageably combined into one database to allow robust interpretations. But I am sure that the good folk of Pages would be up to the challenge. Okay, that's really it now. Just an FYI, the database is currently version 1.0.0, but we will be updating that with some minor fixes sometime soon. And Nick Mackay, I think, is working on a system where authors will be able to submit new isotope data sets to ISO 2K sort of at the same time as you upload your data to NOAA or whatever. Possibly he'll talk about this in his seminar, which is the next one in the series. So I'll leave you just with these nice figures to look at and invite any questions, anything complicated I might field to our leader, Bronwyn. Thank you.
Thank you so much, Georgie. You can just imagine the thunderous applause from everyone who was on the call. This is the only problem with Zoom. So I'm sure that our speaker would be happy to take some questions. If you have questions, you're welcome to either just type them in the chat window and I can read them out loud. Or if you would like to speak your question out loud, you can also type, I have a question in the chat, and then you can unmute when I tell you to. So let's give people a minute to ask those questions. And while you're thinking of your questions and typing them out, I will also just make a brief plug for as many of you know, if you're on the Pages 2K mailing list, we are moving into the next phase of the Pages 2K project and are sending out, if you are interested in helping to lead the next phase of the project, you should have seen an email asking for expressions of interest in doing so. So if you have not seen that email, go look for it and we can put some more information about that online. Oops. I guess if we, I see Ray has his hand up. Ray, go ahead.
Hi, thanks very much for the talk. It was very interesting. Can you tell me, I didn't quite understand how you were estimating effective moisture.
So the records in terms of the isotope interpretation, that field in the database was filled in according to how the authors of the data originally interpreted their records. So for example, a straightforward is lake carbonate, maybe if the author said the primary driver of variability in the lake carbonate delta 18 was evaporation relative to precipitation in that lake, then that would be an effective moisture record. And anything similarly with corals. And so it is a catch-all. It covers things like precipitation amount or evaporation amount. But yes, just anything involving sort of
Okay.
Yeah.
Now that explains why the network is more limited. So, yeah.
Yes. Yeah.
Okay.
Actually, just by the nature of the particular proxy archives, fewer generally of the annually resolved records are effective moisture, although it does catch a lot of the long records, for example, lake carbonates.
Okay, thanks.
Thanks. I see there's a question here about the elevation of the site. Oh, sorry, this is a direct message. This is a question. Is the elevation of the site a variable in the various types of analysis? In what I've shown you here, no, it hasn't been specifically accounted for. These analyses are split only by this isotope interpretation field. It is, however, a field that is very well filled in the database. So if the authors of some data provided information about the elevation, then that is in the database. We also retrieved a lot where they didn't, just from the latitudes and longitudes. So it's an interesting one. They obviously, in a lot of places, that does affect the isotopic composition of the environmental water.
We have a question in the chat from Rafaela asking if there are data sets comparing high latitude snow or glaciated sea and corals or other organisms or salinity.
So that's asking, so comparing the signal at high latitudes to that at low latitudes, I guess, is that? I mean, and that's certainly analysis that you could do. I'm not sure that this has been specifically looked at by anybody yet. I mean, so in the database, the data sets are just there for analysis. But I'm not sure that this specific analysis has been done. I'm sorry, Brahma might know more about that.
You can do it.
Please do, in fact.
Question from Dominic Fleitman. How do you account for potential seasonality biases in different archives, such as trees, corals, lakes, and speleothems?
Yeah, which is an excellent question. And it's something that concerned us isn't the right word, but it's something we were very aware of as we were constructing the database. So we do have a quite well quality controlled seasonality field in the database where we sort of took any author interpretations of seasonality and translated them into standardized terms. So via months. So if it's a JJA signal or a or whatever. In the case of these analyses, we did not specifically account for that. So it's everything in the pot together. I mean, they are also 30-year binned, and I guess our implicit hope is that some of that seasonality would come out in the wash a bit. For more detailed analyses, for example, some things that I'm working on right now, it's definitely something that I'm taking into account. And even restricting records to those where the authors claimed an annual signal, there's still quite a lot of records. Yeah. It's of course, it's a very important consideration when combining all these archives, so that field is well available for. Thanks, Tommy. That's a great question.
Our next question in the chat is from Nikita Kaushal asking, is there a way to check for archive-specific biases in the regional signals?
Yeah, and this is something that we did a fair bit of as we were preparing these analyses. So, I mean, the most straightforward, I guess, thing that we did was to, well, I guess in the case of these principal components analyses, to see if there are particular archive types that were contributing particularly strongly to the first principal component, which is to say in the strength of the loadings. We also did, because I mean, the archive types are tagged in the database, we did run these analyses separately for different archives, especially where we were quote unquote concerned that it might be making a major difference. For example, in the case of the ice cores, potentially bringing too much temperature to the party. But yeah, it's a really good check when you're putting all these things together. Of course, the signal isn't being really heavily dominated by one archive. Yeah.
Question from Laura Hunt asking if there are any significant gaps, such as a lack of records from certain locations or material such as rainwater, seawater, natural archives, etc., within the database that you noticed.
This is paleoclimate, right? There are always gaps. My favorite gap to point out is always the Southern Hemisphere, just as a whole. But I mean, you can see here, there are huge parts of Africa, which is obviously hydroclimatically extraordinarily interesting and important, that we don't have terrific coverage, a lot of sort of Northern Europe. So certainly there are what I would call the classic spatial gaps in paleoclimate. In terms of certain materials, that is a good question and not one that I have considered straight up. I guess you can have a look at this map and see there's maybe fewer groundwater records. I know certainly there are, and you can see here, or actually maybe here, there are some archive types that not dominate, but that there are a lot of things like glacier ice and lake sediments. Yeah. There's always room for more data, is my summary answer to that.
Any other questions for our speaker?
You can see here that we only have 2 mollusk shell records. So if there are people out there making long records from bivalves, we'd love to see it.
One more question has come in to the chat saying some studies pair coral delta-18 and coral strontium calcium on a single coral to deconvolve the temperature signal from the delta-18 of seawater. Are there any data sets in the ISO2K network that contain paired proxy measurements or a deconvolved delta-18 seawater record, which would enable for better paleosalinity reconstructions?
Another excellent question that I'm concerned I'm going to answer badly. Anyway, so in the database, we do include a lot of what we call ancillary data. So things like coral strontium calcium ratios. And I think actually in the case of a lot of records like the corals and definitely the marine sediments, we do also include, if the authors went and did that correction, is that the right word? If they converted the carbonate delta-18 values to seawater delta-18 values, then we also include that interpreted or that inferred seawater delta-18 time series in the record. So in a lot of cases, that's already there to be used. If it's not, generally we do have that ancillary data also included on the database, so you can go and do your own sort of seawater delta-18 reconstructions. And I think, as far as I know, I wasn't on Team Coral, but I think they did a really, really good job of getting all that data and sort of bundling it all neatly so that you can do such things as this. Yeah. I hope I got that right.
Yeah, there is a field in the database where you can filter coral records that are calculated delta-18 of seawater versus the delta-18 of the coral. So that's something you can access very easily. And Hussein Sayani is pointing out that there is a coral Hydro2K database in the works, which was created for this exact reason. And so you can tune into the seminar on October 13 to find out more.
Yes, I'm so sorry that it just slipped my mind, but yeah, a whole database just for corals. Amazing. I'm extremely excited about that.
We have just a minute or so remaining. Are there any final questions? Excellent. Well, thank you so much to our speaker. Lots of wonderful accolades in the chat window. And thank you everybody for attending, and for those of you who are catching up on YouTube later.